We've already done a little bit of modeling with differential equations, but we're going to do a little bit more specifically differential equations that involve exponential functions, okay? We are starting with something that we learned back in Algebra 2, the law of growth or the law of decay, which it wasn't given to us with this rate language, but as we solve this as a differential equation, you are going to recognize it, okay? So the law of growth or the law of decay says the rate of change of a population is proportional to the current population, all right? Rate of change indicates derivative, okay? So this means we've got a derivative of some kind here. It's the rate of change of a population, and this is over time. It doesn't say it, but it is over time here, okay? And it says it's proportional to the current population. So I'm going to write a differential equation to model this, and I'm going to use T for time. I'm going to use P for population. So this says that the rate of change of the population with respect to time is proportional to the current population. So remember, K is our variation constant. All right, so then to solve this differential equation, I'm multiplying both sides by dt, dividing by p. So I have 1 over p times dp equals k times dt. Remember that k is a constant. It is not a variable. So then we are integrating both sides. Antiderivative of 1 over p is the natural log of absolute value p. And then antiderivative of k with respect to t is k times t. K is just a coefficient. And then we need our constant over on the right side. Okay, so then let's solve this for p. I'm going to take the exponential of both sides. Here I have e to the natural log of absolute value of p. Really just gives me absolute value of p. And then I have e to the equal sign equals e to the kt plus c. That the whole thing has to go up into the exponent. I can't just distribute and say e to this plus e to this. That's not how exponents work. Okay, right here, this absolute value of p, because we are talking about the population of something, either population of people or bacteria in a petri dish or whatever it is, we're only talking about positives, so we can ignore the absolute value bars. Really, they would go away with a constant here in a second. You'll kind of see what happens there. But because this is population, not just any function, it is okay to go ahead and ignore the absolute value bars. All right, so then we get that our population is equal to, doing a little bit of algebra exponent property stuff over here, that's e to the kt times e to the c, okay? And then if c means any constant, and I have e raised to the c, remember this is still a general solution, 2.71828, whatever e is, raised to a constant is still a constant. So I can write that as e to the kt times just a constant c. Okay, so I have p equals e to the kt times c. This is a significant formula. It's not really the way that we usually recognize it because the variables are different. But let's suppose that we're talking about an initial population, meaning a population at time 0. Okay, well, if t is equal to 0, then I get that my population is equal to e to the 0 times c. So that means that c is, actually I should put a little sub-zero here. So that means that c, the constant, is the initial population. Okay, so what does this really look like here? This means that the population is equal to and I'm going to move that constant to the front as a coefficient, is equal to the initial population times e to the kt, or the way that you probably remember it from Algebra 2, if you remember it at all, is that p is equal to the initial population times e to the rt. Maybe you remember PERT, okay, the PERT formula. That's the law of growth. This probably came up when you learned a little bit about like simple interest, compound interest, and then like continuously compounded interest is the PERT formula, where r is your rate. That's the same as your variation constant, okay? So that's where this formula comes from. It is by solving the differential equation for the law of growth, which says rate of change of a population is proportional to current population. Okay. Now, once we have that, we could answer some questions that are really not so much calculus, but algebra. Okay. So this one right here is just an example of where we use that. Now, we can start with the original differential equation and solve stuff, or we can just say, yeah, we know that PERT formula. Okay, so here's an example of that. And again, you did this back in Algebra 2. This is calculator active as well. All right, so it tells me that the half-life of carbon-14 is 5,734 years. Let's start with that piece of information right there and write a function, okay? So half-life of carbon-14 is this amount of time. Half-life means the amount of time that it takes for half of a substance to decay. So what that means is I can say my initial population is whatever I want, and then my after population is going to be half of that. I can say 100%, 50%, I can say 1 and 0.5. It doesn't really matter how I do it. I'm going to use my initial population as just 1, and so then I'm going to say 1/2 as the after population. So that's going to be 1 times e to the k times, and then my number of years that it takes for 1 to get to 1/2 is 5,734. Okay. Then from there we can solve for k. This is a calculator problem. I'm going to take the natural log of both sides. So we have a natural log of 1/2. Is equal to natural log of that. So the e and the natural log cancel out. So 5734k. Come on, pen. Then divide both sides. So k is natural log of 1/2 divided by 5734, which is approximately negative 1.21 times 10 to the negative 4th. Okay. Now, if I'm answering the next part of this question, like even if I write k, or even if I write this number, which I could write this as negative 0.00012 if I want. Even if I write this, I'm going to keep that number in my calculator, and I don't want to round until the very end. Okay, so keep that in mind if you are doing calculator active problems. All right, so now this is I can plug back in and write a function. So my function for this particular what is this? Molecule? Carbon-14. Okay, element? Molecule? You know, whatever. Okay, ask your science teacher. All right, is going to be that the after amount, I'm just going to use A, is equal to the initial population. So we'll say P sub 0, okay? Or I guess I could use a P there since I did up there. Who cares? All right, times E to the negative 0.00012 times T. All right, that is the function that is specific to the half-life for carbon-14. Our question is, a fossil that has only 5% of the amount, how long ago did it die? So our initial amount we're going to say is 100%, which is just 1 as a decimal, and 5% is the current amount of carbon-14. So I'm going to put that in for A. So I've got 0.05, that's the 5%, is equal to 1 times e to the negative 0.00012 t. Again, I'm not actually typing that, I'm just using that. Take the natural log of both sides, divide by the k value, and we get that t is approximately 24,782. I am going to round this because obviously, I don't need to go to 3 decimal places with a problem like this. So what are we really saying? We are saying that it is about 25,000 years ago is how long ago it died. Okay. All right, let's do one more example. This is not a law of growth problem, but it is a differential equation involving exponential growth. And then we'll just do one more example in this video. Okay, so here we have fish being introduced to a lake. It says the change in the rate of fish, so the change in the rate of f, so the derivative with respect to t, so that's derivative of f with respect to t, is directly proportional, don't forget your variation constant, to 900 minus f, so the difference between 900 and f, okay? And it says t is measured in years. All right, when t equals 0, there are 400 fish in the lake, so that's giving me like an initial condition. 0, 400 is my initial condition. And then it also says 3 years later, there are 600 fish in the lake. So at time 3, we have 600. Okay, so we can use that to solve our differential equation. And My apologies if there's not a ton of room on your notes for this particular problem. It might have gotten a little bit squished when I was printing it. All right, so how do I solve this? Well, I'm going to get the f stuff to the left, so it's going to be 1 over 900 minus f times df, and that's equal to k times dt. And then, whoa, going crazy. Let's integrate both sides. Okay, so then we have the integral of 1 over 900 minus f is not natural log of 900 minus f. It is negative natural log of 900 minus f. Why the negative? Because my u needs a -1 df as the du. So I would multiply by -1 and -1. Okay, so please pay attention to any possible coefficient changes that you need there. All right, and then that's equal to kt plus a constant c. All right, and then I'm going to go ahead and solve for c first by using an ordered pair. Okay, I'm using my initial condition, which is 0, 400, and I'm going to plug that into this. So I get, actually, I'm going to move the negative to the other side. So I get natural log of 900 minus f is equal to negative k times 0 plus a constant. All right. And so that's 0. Okay, so, oh, no, I forgot to plug my, sorry, back up, plug in 400 right here. Let me do this in 2 steps. Natural log of 900 minus f is equal to negative kt plus c. Okay, now I'm going to plug my 0, 400 in there. So I get natural log of 900 minus 400, which is 500, is equal to 0 plus c. So c is natural log of 500. Okay, plugging that back into this, I get natural log of 900 minus f is equal to negative kt plus natural log of 500. That's my c value. And now I'm going to solve for f. Okay, so to solve for f, I'm taking the exponential of both sides. E to this, that cancels out. So I have 900 minus f, absolute value bars, is equal to e to the negative kt times e to the natural log of 500. Remember the properties of exponents here. It's not going to be e to this plus e to this. It's e to the entire quantity, and then I can break that into 2 bases. All right, so that's going to cancel out over there. Okay, so we've got 900 minus f is equal to, I'm taking the absolute value bars off of here, and I'm going to put a plus or minus on the right side. So I've got 5, this is just 500 as a coefficient. I'm just doing a bunch of algebra right now. 500 with a plus or minus, and then e to the negative kt. Woo, okay. So now I'm going to use my second point, which is 3, 600. I'm also thinking I probably could have plugged it in back here to solve for k, but that's all right. I'll just keep going where we are. It might have been a little bit more efficient if we plugged it into this line, but that's okay. All right, so we get 900 minus 600 is equal to plus, well, it's going to be positive, okay? So I don't need the plus or minus anymore. 500 times e to the negative k times 3. Okay, so that's 300. 300 divided by 500 is 3/5. E to the negative 3k. Natural log of both sides, so natural log of 3/5, and then that gets rid of this. And I'm going to divide by -3. That's going to be my k value. Okay, and once again, I am going to plug that into a calculator, and we get that k is approximately 0.1708. Okay, going back to here. Going back to here, I'm going to isolate the f by moving the f to the other side and moving this whole thing to the other side, or you can subtract 900, divide by -1. It doesn't matter. Either way, I get capital F is equal to 900 minus 500 times e to the negative kt, so negative 0.170, come on pen, 1708 times t. Okay, I did do kind of a lot of algebra in some of those steps. We probably could have used the calculator a lot sooner, maybe not gone quite so far doing it by hand, but either way, we should get to that same function. If you have any questions on any steps that I skipped or anything like that, just let me know. Okay. All right, so this is the function. This is the particular solution to our differential equation, but this is the function that describes this solution with the fish in this particular lake, okay? So now the question says find the fish population in another 3 years. And because it says in another 3 years, that means after 6 years total, okay? So we're just going to plug in t equals 6 here. So f equals 900 minus 500 times e to the negative 0.1708. I'm going to use the number stored in my calculator there, times 6. Again, calculator problem, that comes out to be approximately 720 fish. All right. And then last question, find the limit as t approaches infinity of our function f of t. Okay, so limit as t approaches infinity of f of t, which is 900 minus 500 e to the negative 0.1708 t is equal to, that's going to be 900 minus 500 e to the, okay, so as, actually I'm going to leave that part off for a second. If t is approaching infinity, I have negative something times infinity is negative infinity, okay? E to the negative infinity would be the same thing as 1 over e to the positive infinity. That's going to approach 0, okay? That's going to approach 0, right? So minus 500 times something that approaches 0. That's going to be 900. Okay, so our limit as t approaches infinity is 900. What does that mean in the context of this problem? Okay, so as time continues forever and ever and ever, f of t, which represents the number of fish in the lake, cannot get any, well, it approaches 900. It cannot get any bigger than that, which makes sense because if you have a finite amount of space in a lake, you can't put an infinite number of fish in there, okay? But this is what is called the carrying capacity, okay? Which if you remember anything about logistic growth, if you learned that, then that should sound familiar. But really what this means is that the lake can hold about 900 fish. Okay, that's its capacity. Okay. All right. This last question, it does give Newton's law of cooling, which is this function right here, this differential equation. This is not something you would ever have to have memorized. If there was a question involving it, it would be given. And there is a question down here that applies this, okay? T sub E is the environmental temperature. T sub 0 is the temperature of the, T sub O is the temperature of the object. And there, so this is just another example of solving a differential equation involving an exponential function. It is a little bit, kind of long in the algebra. It's a little bit tedious. I'm not going to work this out in a video, but I will post the solution to that. So give it a try and then you can check your answer.